So could be that the problem is also the big noise that is coming from the roof. So let's hope that is getting better going on during the day. All right, so the topic we are dealing with is the dynamics of continuum. And the continuum with which we are working will be the tensioned cable and the bending beam. So those are the two objects with which we are working, because they is not working. Okay, is it working now? All right, so I think that you have a very simple, an intuitive view of what is a continuum. I think that there is a background in your studies. I underlined what was a little bit mentioned in the set of questions that we asked you to verify. So we asked you to answer to a list of questions, and those are the prerequisite in order to follow currently the course. And so into this prerequisite, there are also the knowledge of the static behavior of the bending beam. In my opinion, it is absolutely necessary that the people who doesn't make the Euler-Bernoulli equation for the bending beam should try to fill the gap. So we will not fill the gap about that. We are using what is needed about the Euler-Bernoulli theory of the bending beam in order to deal with dynamics. But we will not repeat the theory of the bending beam according to the Euler-Bernoulli formulation. So for what concerns the cable, the tensional cable is much more simple, because there is almost any theory. There is no theory at all. And so we have a very clear, intuitive vision of what is the cable. And so I made a drawing here that should be representative of what is a cable, but it is exactly the same drawing that I should have done in order to represent a beam that is undergoing transversal vibration. So it is, we will deal with slender beams, slender cables, and the drawing apparently is exactly the same. But the reason why then we can have a dynamic behavior, a vibrational behavior, is due to a stiffness, where the stiffness, the reason for having the stiffness is totally different in the cable and in the beam. The reason why we have a stiffness that is allowing a dynamic behavior, and we should have the intuitive vision that vibration means always a contraposition of stiffness with respect of mass. All right, so in order to have a some dynamics, I need to have a mass that is undergoing, that is constrained through a stiffness. Because of that, then we are making experience of a dynamic behavior. All right. So there is the stiffness, there is the mass. The mass is distributed, and the stiffness in the cable is just given by the tension, and we will learn step by step why the tension is giving this stiffness. All right. At the moment, we don't care much. So we, for sure, for making the theory, we are not addressing at the first step the real object, but we are addressing a idealized, very simplified version of this object. And for example, for the tensional cable, the hypothesis, the simplification hypothesis with which we are playing will be rectilinear shape, tension and mass per unit length constant, no shear in bending transmitted. So we are assuming that this idealized cable is not able to transmit any bending action, any shear action, all right? So the idea is that, for example, at the constraints, we will not have any bending, whatever is the constraint. Although if I am attaching the cable with a fully constrained version of the constraint, it is not able, it is the cable that is not able to transmit any bending and any shear, okay? This is the key idea. Then, and we are using, in order to develop a very simple theory, we are developing all of that. We are using those hypotheses. Then, when we are setting, in the moment in which we have this object that we understand is undergoing the vibration, we are assuming that there is negligible damping, negligible internal damping, and so this vibration will last forever. And then we are speaking about small vibration amplitudes. All right, all of that. So I listed those hypotheses just to mention that we will play with that. But what is most important is to criticize those hypotheses. So it is totally wrong if now I start developing the theory and using this hypothesis to write equation and that's it. All right? It's wrong. It's wrong because it is important to show why we can assume all of that and which is the difference with respect of the reality. For example, the drawing that I made here is following the very first one, the rectilinear shape. But is it possible to have a tensioned cable undergoing a rectilinear shape? And then the other point is, if we were following the third rule, no shear and bending transmitted. So if we ask to this object to not to transmit any bending and any shear, is it possible to have the shape that I draw here? There is something very wrong here in this drawing. Because, for example, I forgot to say that we are working into the gravitational field, all right? So all what we have to work with is undergoing the effect of the gravitational field. And so there is a total force that is acting on this cable. The gravitational force, mass per unit length. So I assume that m small cap is the mass per unit length, kilos over meters. So the total mass of the object is m multiplied by L, where L is the length. And so I have a total force. Where are the reaction of this force? In which way I can play with the constraints in order to support the cable? So I could say that here I have a vertical force that there is one middle, one half of that, and here another force that is one half of that. But it is not able to withstand any shear, all right? So I cannot put a transversal force here. If it was a beam that is able to transmit shear and moment, of course I can have a shear, I can have a force transmitted here. I could have a bending moment, but because it is a different object, we have to imagine the cable like an object like that, like this, that is totally unable to transmit any shear and any bending, all right? So there is something wrong. And so the only way to do in order to satisfy those conditions is to contradict another hypothesis that is the very first one. That is to say that the actual configuration of the cable, whatever is the cable, whatever is the tension that is applied to the cable, the only way to have it into the gravitational field is to have a configuration like that, to have a tension that is according, that is in agreement with what is mentioned here. So I have the tension, but I don't have any bending moment. I don't have any shear. And this tension is allowing to take the load, the static load. The only way to support the static load is to make so that this static load is supported by the tension. All right? So I draw alpha as the angle with which I have the cable arriving to the constraint with respect to the horizontal line that I suppose that the connection between the two extremities is horizontally configured. And so that this angle alpha is I make the hypothesis to have symmetry, of course, everything is symmetrical here. And so this, what happens is that the condition is that so what is happening is that the angle alpha with which I'm playing is consistent with the balance of the vertical forces. So one half of the total vertical force goes here, the other half goes here, all right? So tension sin alpha is the vertical force that is making the equilibrium to total mass multiplying the gravitational acceleration, all right? And then what happens? It happens that in the middle, if I'm breaking here, let me see which so finally, the force that is applied here, so the horizontal equilibrium of half cable is saying that the tension that I have in the middle is giving the equilibrium to the tension at the extremity multiplied by cosine alpha. And so this is So finally, working with those very, very simple ideas, what happens is that if I want to use the concept no share and no bending transmitted, and then I want to apply all of that into the gravitational field, I cannot have the straight line. I must have a configuration like that. It happens that at the constraint, the tension I have in the cable cannot be equal to the tension that I have in the middle. It's absolutely different. It's different. Of course, all of that goes in the direction of having those hypotheses verified, just in case tension at the location L half or at whatever location, or at the location there, whatever is the location, is much larger. I would say like that. So it is not necessary to specify 1/2. So I could say that sinus alpha is equal to the tension at the location L divided mgl 1/2. All right. And so I can say sinus alpha goes to 0, and so alpha goes to 0, and so the cable becomes a straight line in case the tension at the location L is much larger than mgl. But it doesn't matter to have, if it is much larger with 1/2, it is much larger also without a 1/2. It is not strictly necessary. So we understand that the condition for having a shape that is as much as possible rectilinear in the gravitational field is that the tension with which I am pulling the cable is much larger than its weight, all right? Otherwise, so whatever is the tension with which I am pulling is not a straight line, is not horizontal. There is a curvature, there is what we say a catenary. One second to All right, so in a very, very quick way, we represent the equation of the catenary. Just to say that when you are tensioning a cable that is showing itself with a shape that is given by the tension you are positioning into the cable together with the effect of the gravitational field, what it happens that this cable is assuming a shape that is called a catenary, all right? The cable, the attitude, the appearance of the big cable of a suspension bridge has exactly the catenary shape. For which reason? Because it is into the gravitational field, but is the gravitational field the real responsible for the shape of the catenary of the suspension bridge? Yes, but not through the mass per unit length of the cable. Also through the mass per unit length of the cable, but also through the mass per unit length of the deck, the mass of the vehicles over. Somehow there is a distributed mass, a distributed load on this cable that is not so different as the mass per unit length was increased by a factor that is taking into account the deck together with the to the paying load, what is called the paying load. So that the shape of the cable of a suspension bridge is quite similar to a catenary, not exactly the same. And which is the equation of the catenary? It is interesting to say that it is very, very simple. So the equation of the catenary is this one. The derivative at the generic location x, but it comes very, very simple if we are using the curvilinear abscissa, all right? So using the curvilinear abscissa, that is the measure of the cable with respect of a reference location where we say that is 0. For example, here I made 0 here, S equal 1/2 the length of the cable, S equal to the full length of the cable, all right? But I could have also made a different choice to take the 0 in the very middle, where is the lowest point, so to position the reference system over here. So if I'm working with this reference system and I am positioning the 0 of the curvilinear abscissa here, I am making this drawing. It is interesting to take into reference this point, because this point is the point where I have the lowest tension into the cable. Because the tension must increase because I have more mass to take over, okay? So I am continuously increasing the tension of the cable going up because I am adding other mass to be suspended. All right, so making reference to this location where I have the lowest tension, the tension in the middle, the tension at the lowest point of the cable, I am saying that this force is giving the equilibrium to the tension at the location S multiplied by cosinus alpha. And the total vertical, that is mass per unit length, gravitational effect, and length of the cable. Be careful that this is the length of the cable, not the distance over the x-axis. So we are working with a curvilinear abscissa that is making very, very simple the calculation. Then we stop here because it becomes more difficult. And so the vertical, the total vertical, so the tension at the location S multiplied by sinus alpha is the total mass the total mass of this piece of cable. And so we say that making the ratio among the two forces, this and that, I am calculating the tangent of the angle because the tension T at the location S is cancelling. And so I'm writing this one divided by this one is the tangent of the angle. And so the tangent of the angle is dy over dx. So I am mixing the coordinates. I'm saying that into the Cartesian axis, the derivative into the Cartesian axis, so dy over dx, and now I am adding here the curvilinear abscissa, so I'm adding a different, of course all of that is linked, but the mathematics to ahead, this becomes more tricky. So this tangent is equal to the total mass that I have into here, divided by the tension at the lowest location. All right? So is the derivative is let's say, we could say, the derivative measures the ratio of the weight of half the cable with the tension in the middle. So the derivative is a measure of the ratio among the tension at that location. Sorry. Cancel what I said. So the derivative is measuring the ratio among the total weight of this piece of cable with respect of the force acting at the lowest location, that is the extreme. Or there is another more elegant way of representing, that is saying that this quantity mg and T0 are playing together, and so T0 divided mg is a length, of course. Is a length because dy over dx is non-dimensional. So dy over dx is non-dimensional. This is Newton. This is Newton over meter. And so T0 divided mg is length. So this is what we call A. A is the length of a cable having a weight equal to the T0 action in the middle. And so the derivative at the location S is the ratio, is measuring the ratio among the actual length of the cable and the length of an equivalent cable having a weight that is equal to the total force in the middle T0. And so the equation of the catenary is dy over dx equal S divided A. That's it, it's finished. So what is the mathematicians like to speak in this way? Very, very simple, absolutely simple. So it is the ratio among two lengths. The length of this piece of cable versus the length of the equivalent cable having a weight equal to this object, that is T0. Okay, but this digression is just to say that the shape of a cable into the gravitational field is always a catenary, cannot be a straight line, all right? Cannot be a straight line. And so we are making criticism toward the hypothesis. Never believe to the hypothesis with which the people are asking you to play your thinking. You must always say that maybe they are wrong, all right? Very well. So, all right. Of course, if you made had a view on the papers that I uploaded, for sure you know that it seems that it's possible to have the possibility to, into the gravitational field, to have a cable that is taking the shape of a straight line. All right, it is the same cable, mass per unit length m, 0, L, gravitational field. It has a straight line, fantastic. All right. What is wrong here with respect to the hypothesis? The tension cannot be constant. The tension cannot be constant because if the tension here, T at the location X is equal, let's write here, T at the location X is equal to tension at the location 0 plus mgx, all right? So it is growing, because I have to pull up the weight of the cable itself, all right? Again, the hypothesis of having also T is going to be constant, again, in case T0 much larger than mgl. So, and who is this T0? Is the tension wherever it is, wherever it can be, the tension over here or the tension down here. If the tension is much larger than the weight of the cable, if the tension is 1,000 times larger of the weight of the cable, the tension is constant everywhere unless an approximation of 1 over 1,000. All right? Is it clear? So the way in which we are looking to the hypothesis must be not to look at the hypothesis like something that is very bureaucratical, but to something to which we have an approach that is an engineering approach. We are never doing the calculation perfectly, exactly corrected. There is always an approximation. There is always a mistake in what we are doing. All right, and so it is possible to make a good calculation, assuming that the shape of the cable is rectilinear, although there are some approximation, although the shape is not perfectly linear. All right, and then we must be quantitative. Let's say, in any case, that it is fundamental for our purposes to remove the reality of the cable, that is to have a shape that is not rectilinear. So we must train ourselves with this hypothesis, with the hypothesis of tension constant, mass per unit length constant. It is necessary in order to understand the way in which all of that is working, all right? And so the real reason why we are making those hypotheses is in order to have a mathematics that is able to approach the problem in a very simple way, and so to deal with that, having, in any case, having the flavor of what is happening, that is a very good approximation of the reality, knowing which are the in which way we are bringing, we are making the ideal solution that is an approximated solution into the direction of it be quite a good solution. And so this is a fundamental step. If the tension is much larger of the weight, the hypotheses with which you are playing are quite valuable. And then there is another point. So this hypothesis is interesting. So in case the tension is much larger of the weight, all right, we are getting closer to the idealized configuration. Then let's say that of course, being the tension constant, we made all the criticism that is possible to make. So due to the catenary is changing the tension, also a straight line having the weight distributed is changing a little bit, not much, and so we have an idea that the tension could be not really constant, but we have also a measure of which is the error that we are making. The error is hidden into those formulas that are shown here. No shear and no bending transmitted. This is more technological. So at this point, which are the cables that are able to transmit shear or to transmit bending? The real cable with which we are playing are able to transmit really bending. The answer should be, the only way to understand that is to take in our hands a cable, a real cable, and to see if the force in order to bend it is large or not. All right. Surprisingly, if you are taking your hand, for example, some of you are a good skier. I think so. There are plenty of skiers, and so the cables that are running in the how do you call it? Cable cars with the single wire that is going around, and with the vehicles that are attaching and detaching. This cable, in your opinion, has a relevant stiffness, bending stiffness, negligible bending stiffness. Which are the cables who, for example, in the cable cars with the two typology of cables, the one that is taking the vertical load, the other one that is taking the horizontal, the pulling load. Portante and traente is the word in Italian. So in which of those cable car system we can have an example of something that have a very important bending stiffness added to the behavior of cable? In which one is large, in which one is small? So the answer here is very technological. So, of course, in a cable car where you have one single cable that is continuously making continuous rotation, because it is continually going up and down into the pulleys, and it must have not bending stiffness. It must have a very, very light bending behavior in order to make the work for which it is designed, that is the kinematics of the complex kinematics that it has to follow. But for example, the fune portante, I don't know how to translate in English, the big cable that is taking the vertical load of the very, very large cable cars that are just one way up and down without being detached. So this big cable there, could have a very, very large stiffness, because it is designed not to undergo like small angle, great angle of rotation. All right. So it depends on the technology. All right. But for sure there is a bending effect into the cable, and the real modelization of a real cable must take into account all of that. And so the modelization with which maybe you will play using the piece of code that we are giving to you in MATLAB that already have some modeling are taking into account of a tension, of a stiffness due to the tension, but also a contribution due to additional bending effect. All right. And so finally, we will study the tensioned cable, the bending beam, that with a theory that is very idealized, and then we will study the tensioned beam. So the tensioned beam is the real model of a cable where we have together the stiffening effect of the tension plus a possible contribution of bending, and the tensioned beam could be also a real beam that is designed in order to withstand loads due to relevant bending moments, but with an additional stiffness given by axial forces. And so we must be conscious that in case we are adding relevant axial forces to what has an idealized behavior as a beam, we are changing the behavior of that beam, and we are mixing the two things, the dynamic behavior of the cable plus the dynamic behavior of the beam, and the two things are playing together. So we will try to give you a flavor of all of that, developing the theory of the two objects separately, one from the other. Let me see if there is something that is, yes, there is another hypothesis, the very final hypothesis. Small vibration amplitudes. What does it mean, small? So specifically for the dynamics, I think that, I don't know if you made a lot of dynamics, yes or not, But in many application fields, you are told that under the hypothesis of small displacement, and then, let's say, small displacement means infinitesimal displacement, this theory is applicable. And here we do the same. So all what we are saying is under the hypothesis of small displacement, we will work with constant tension and ahead. Well, has anyone played really with infinitesimal vibration, infinitesimal displacement in an engineering field? Infinitesimal in the way that the mathematicians are working with? Absolutely not. If it is infinitesimal, it is at zero for the engineer. Otherwise, we have a measure of all of that. So we are never working with infinitesimal displacement. Never. Never, it means never. Because we are measuring. If it is vibrating, I pretend to measure something, and it has a finite value. If the cable is undergoing a vibration, I am measuring how much is vibrating in the middle, how many millimeters, or fraction of millimeters, but it has a quantitative, finite value. So what we can argue that becomes small is the ratio among this quantity and, for example, the total length of the cable. So we could say that it is small when it is 1/1000, the displacement in the middle with respect of the length of the cable, or 1/100, all right? And we will give you a practical example of a cable really measured, in which we are working with real vibration that we are giving vibration to the cable, and it looks like it is perfectly linear, the behavior, and undergoing a perfect correspondence with respect to the idealized. But then it will be possible to look at very clear effects of nonlinearities due to those amplitudes that are not large, but let's say not negligible. So in this example, the length of the cable was 50 meters, and the amplitude in the middle was plus minus 20 centimeters, something like that. And so the percentage of the amplitude was 20 divided 500, 50 multiplied 100. So 50, so 5,000 divided by 20. So I say 20 centimeters, 50 meters is 50, 500, 5,000 divided by 20. It is 1/2500, isn't it? So if I say 20 centimeters with respect to 50 meters, it is 1 divided 2050. So with an amplitude like that looks like, did I make a wrong calculation? Is it okay? So you are much more fast than me doing all of those calculations. So is 20 divided by 50 meters, 50, 500, no, I'm wrong. 50 meters, 50. No, I'm wrong. It is 1/250. It is 20 centimeters over the length of 50 meters is 1 divided. But people, if I'm making something wrong, you must tell me, right? You must tell me. If someone made the calculation, is saying you are wrong, all right? It is helpful for me. It is helpful for all of you. So it is 1 divided by 250. And so it is not totally negligible. What we are looking at in this case is that the natural frequency of the oscillation at small amplitude is measurably different than with large amplitudes. And so this question of the small vibration amplitude is something that is in the vibration becomes relevant, is negligible somehow, but it is negligible in case it is negligible the error that with which we can withstand. All right. Finally, and then we start another step. We are speaking about the continuum, and we are developing some theory, a theory that it looks like being very, very different with respect to what you are used to do with 1 degree of freedom system and n degree of freedom system. All right. So you have the idea of the n degree of freedom system, and it is very easy to deal with the n degree of freedom. It has a very practical meaning. It shows that with the equations that are matrix equation, so we can work with that. In the continuum, the number of degree of freedom that we should play with is infinity. But let's say that the final purpose of the theory that we are developing is to show the real purpose of those theory, of this course, is to make you aware that it is possible to deal with the continuum, finally making calculations in n degree of freedom. And we will start playing with the continuum, and just a little bit after, we will never play with the equation of the continuum made analytically in the way that is shown by the mathematics. But we will always finally have the possibility to make a discretization. And the discretization is the conversion into principal coordinates. So if you did the n degree of freedom system, you should know that it is the possibility to speak about modes of vibration and principal coordinates and the modal approach. All of that is that what you did in the n degree of freedom system is totally equal to what can be done in the continuum. So the continuum is extremely interesting because there is a very powerful way in order to make the discretization is to change and to work in principal coordinates. And so the number of principal coordinates is limited, and it is the natural way of making a discretization. And so this concept of principal coordinate of model approach that you developed into the n degree of freedom system will be the fundamental tool in order to have the intuitive view of what is happening when you have a continuum that is vibrating. But then there is another toy that is the most valuable toy that, in my opinion, some of you is already using, also without knowing any theory, but it works and it is very simple. That is the finite element method. So if you are making let's say, the CAD drawing of a structure, and then you apply in this CAD system the information about the stiffnesses of the single pieces, the mass quantity that is described in the pieces, then you push a button and you ask for the dynamics. And it gives you the dynamics. And you have the dynamics. You know in which way it works. And when you push this button, what is happening? It's happening that the system made automatically the modelization made a finite element model of this continuum, and then the finite element model is intrinsically an n degree of freedom system. From the dynamic point of view, it is, but the n can be very, very large, but it is an n degree of freedom. And so we, at the end of the day, what we will play with the continuum in order to have a modeling of the small pieces, of the finite element pieces, with which we are working into the modelization of the continuum through a finite element model. And so finally, we will speak always about n degree of freedom, but having the knowledge of what is behind, that is at least some intuitive view of the continuum. So we stop 5 minutes and I make some drawings, and so we go ahead, and then we go ahead. All right?
Sì, no, per questa cosa anche 9 sei. Dopo sabato lo richiamiere. Inizierei a scrivere. Adesso veramente. Lo so, è stato
Okay, so we start back. Well, so now what we do is to write the mathematics of the idealized configuration. And so what we say that we are working with an element of cable having a length dx, infinitesimal length dx. This element can undergo bending without giving any reaction. So I am drawing this object with a different angle here with respect of here, and the only thing that I put as a reaction, as an internal action, is an axial load. So the tension is the only internal axial action, the tension, the axial load tension is the only internal axial action that I have to show on the section that I am with which I cut this piece out of the body. All right? And this force is directed along the tangent. So the direction of this force is the tangent of the cable. All right? Then the mass per unit length, the m is the mass per unit length. The hypothesis is that it is moving just in the vertical direction. It is not moving horizontally. So we are working with the transversal vibration of the cable. That's it. So as an effect of the second order derivative with respect of time, and let's say that we must have in mind that the unknown of all of that is the function displacement function of space and time. Okay, I have this the cable that about which we made the drawing before. So this object that we are drawing as a straight line now, with all the back thinking that it is not true, but it is like we make so that it we believe that to make the equation as we were very far away from the Earth, so no gravitational effect and so on. And so the unknown is the function displacement transversal as a function of space and time. This is our unknown. Well, the second order derivative, the second order partial derivative, and here we turn on the light on the mathematics. We must know that the partial derivative is something that is existent. All right, we are working with the partial derivative. We must be able to make the fundamental basic calculation with the partial derivatives. So we know that we can take a derivative with respect of one of the variable, with respect of this other variable. We can take the first derivative with respect of x. It means that dw over dx is the tangent of the configuration of, is the tangent of the instantaneous configuration of the cable. At a certain time t0, I have a tangent in this section. It's given by the partial derivative with respect of the variable x calculated at the time t0, at the time t, at the running time. So I have the running time, and I'm writing the partial derivative with respect of x, that is the running time tangent of this moving cable at the generic coordinate x. Of course, the tangent on the left is different from the right, because I have incremented quantities on the incremented location, and so the transversal force, that is the projection of the tension on the left, is T dw over dx calculated at the location x. This is the projection of the tension on the left side along the vertical direction. The same calculated at the location x plus dx is the vertical component of the force of the force on the right section given by the projection of the tension along the vertical direction. But we also have an acceleration. And so the second order partial derivative of the same function with respect of time is the local acceleration of the body at the location x, all right? So, of course, the acceleration at this location is different from the acceleration in another location. And so we are taking the partial derivative with respect of time calculated at the location x. The second order partial derivative is this acceleration. All right, m multiplied by dx is the element of mass, multiplied by second order d2w dt second, the second order derivative of w with respect of time times, is the elementary inertial force at that location. All right, we make the equilibrium. 1, 2, 3. Projection along the direction, the vertical direction. We write that the total force that is going down, inertial, is equal to the total going up. All right? On the right, the body is the force is going down because it is the inertial, the total going up. What is going up is on the left side, dw over dx calculated at the location x, plus what is going, sorry, it is minus, this is minus, this was going down, okay? This is going down, this is minus. This is minus, and on the right side it's going up, right? This force is, I'm assuming that the tangent here is equal to that one, but with a small increment, all right? So I'm making the drawing here of t, dw over dx, that is a component that is going down. Here the component is going up. I'm working with an incremented value of the tangent, all right? I'm assuming that on the right side, at the incremented location x, I have incremented the values of everything. Acceleration, first order derivative, and whatever. All right, and so I write that at the incremented location, the derivative, using the Taylor expansion, is given by what I have on the left, so sorry, cancel what I said. My intention was to write what I have on the right minus what I have on the left. All right. So I started on the right. Cancel what I said. I'm starting writing what I have on the right side. All right. And then I subtracting what I have on the left. This is the intention. And so I want to write the projection of the action of the tension on the right side. And so I'm using the Taylor expansion. So I write that at the incremented location, the projection, that is t dw over dx, is what is calculated at the not incremented location, plus the derivative with respect of x of the quantity, calculated at the location, multiplied by dx. We are adding at the location x, calculated at the location x. So I am writing here the Taylor expansion of this quantity, that is t dw over dx, calculated at the location x plus dx. Okay? We cancel the gravity component because we say that we are neglecting the gravity. So it is a constant force. It is a constant force that is just giving an attitude that is not horizontal. And so the point is, I want to add the effect of the gravity and to make everything perfectly working exactly the same way that is the real. All right, I have to say that all of that is happening not along the straight line, but along the catenary. So the mathematics is exactly the same, but all those calculations are made along a deformed shape of the object. All right. So now we are canceling all of that. We are saying it is horizontal, and we are canceling the effect of the gravity. All right. And so, sorry, because it was written here. So here it was written the the vertical projection of the tension at the incremented location is Taylor expansion. The quantity calculated at the location 0, so it is calculated at the location x. Okay. Calculation at, because usually we write a Taylor expansion around 0. Here we are calculating this here at the 0 increment. Okay, and in the incremented location is what I have in the non-incremented location plus the derivative with respect of x of the quantity multiplied by dx. And so I write the incremented value of the transversal force minus the not increment. This quantity is cancelling this quantity, and what is left is the derivative with respect of x of the projection. All right? So I prefer to do the calculation like that instead of in the school book you find everything, you find the simplification made in the very beginning, sinus, cosinus, this kind of things. I prefer to do the way in which these things are done by the mathematicians. So to make very, very simple the writing, so to write as minimum as possible, and to write the concept of the Taylor expansion, where the concept of the Taylor expansion is that I write the quantity, not incremented, the derivative of the quantity, and here the derivative of the quantity, it is the derivative of the product of the quantities, all right? And so I write that the general partial differential equation that is representative of the behavior of the tensioned cable in a very general way without having to make any hypothesis with respect of constant mass per unit length, constant tension. Here we didn't make a hypothesis of constant tension. We just made a hypothesis that we have just the axial action. That's it, and not bending and not shear. It is the only hypothesis is that one. So it is very, very general, this writing. And so at this point we go ahead. We go ahead, so we take the derivative. Taking the derivative, so we must know in which way we take the derivative with the partial derivative. I have to take the partial derivative with respect of x of the first, keeping the second constant, and so I write dt over dx multiplying dw over dx, and then I am adding the derivative, partial derivative with respect of x of the second, keeping the first not constant, all right? And so we write tension multiplying the operator partial derivative with respect of x applied on the first order, and so it is making the second order. Okay? I am applying the operator partial derivative with respect of x to the two, on the single element of the product. It is the rule of derivative of a product of function, and the partial derivative, that is, we must take the derivative just with respect of that value, of this quantity. And so the second way of writing all of that is this way. So this is the partial derivative equation that is a little bit more developed. Here it is clearly shown that in case the tension is a function of x, this quantity is not null. And so in case we are making the assumption that the tension in the cable is constant, we know that if it is not constant, we are discarding this quantity. So we know which is the error that we are making. We know the approximation, all right? Every time that the tension is not constant, we know which is the error that we are making into the calculation. And so next, in case we are working with constant quantities, constant tension and constant mass per unit length, we write in this way. We could write in this way, although m is not constant. All right. Because we say that the t is constant, so this is disappearing, and we write that, but the mass per unit length could be also not constant. So this equation written in this way with the mass depending on x is a correct equation with the just hypothesis of t constant, but m could be not constant. In case m is constant, then this quantity, t divided by m, is one single number, whatever is the location in the cable. And now we are playing with the dimensional analysis. So this is another recommendation. In whatever point in our calculation, we stop and we make the dimensional analysis. Always. You will be asked to do that during the exam. We stop in whatever point and we check if it is consistent what we are writing in terms of dimensional analysis. Always. We must be aware about what we are speaking. Always. It must be consistent. What is on the right must be equal to what we have on the left. So if there is a mistake, we find the mistake in making the dimensional analysis. And so what is this C, this quantity C that we are writing, and for which reason we wrote C squared here? We write as C squared because it is the square of a velocity. And because C squared is equal to T divided by M. T is the tension, that is Newton, so kilos, meters, second power 2. Mass per unit length is kilos down here, divided by meter. Kilos is cancelling, so it is meter per second over second, power of 2. So it is the square of the velocity. All right? And so we call the quantity T divided by M C squared. And so the equation written in this form is the partial derivative equation that is driving the vibration of a very simplified cable, where we are making the hypothesis of all the hypotheses that we made at the very beginning. Straight line, constant mass, constant tension is represented by this partial derivative equation. And so what we do with this equation? We are looking for a solution. Of course, this partial derivative equation is saying almost nothing about what is the behavior of the cable. It is just saying that the way in which it behaves, the way in which is behaving the unknown, that is the object of the searching. So this is the object of the searching. Whatever is doing, in whatever way we are writing, it must satisfy. This partial derivative equation is a necessary condition. It is necessary that it is satisfied. Of course, there is something more that it must satisfy. We have to add something more to the problem in order to write how it works. We have to add the constraints. And so, for example, if this is the unknown solution, we are writing a problem. So we are writing a problem where this is the unknown that should satisfy the specific condition with which we are playing. And that can be very different case to case. And here the specific condition could be that W X whatever is time, the solution that we are searching for, W0, so the actual solution, or W0 is the actual solution of the problem. Whatever is time, it must satisfy the condition to be null at 0 and L. Then, for example, a typical problem with which we could play could be that we are giving to this cable an initial shape. For example, we are giving, so this is a very, very ideal way of thinking, because it is very difficult to say that I am giving an initial shape like that to the cable. So it is an ideal way of thinking, all right? But it becomes very, very true in case we are hitting the cable with a hammer. If I'm hitting the cable with a hammer, this is very realistic. But it is very realistic, but we have an additional part that is making difficult the solution, so we cannot make an example. That is that there is a velocity. So here, with respect to what is happening in the case we are hitting the cable with a hammer, giving a very impulsive initial condition, is that in the initial condition we cannot say that in this deformed configuration the velocity is null. Okay. Instead, we are proposing a solution for this problem, saying that at the time t0 we know w function of x at the time t equal 0 is equal to a function f0 function of x. So this could be a well-defined problem. So we are saying that at time t equals 0, we are hypothetically giving an initial condition like that to the cable, and then the cable is evolving. This condition is absolutely very, very similar to what is happening if I'm hitting the cable with a hammer. We could say that when I am hitting the cable with a hammer, there is an instant in which the cable could have somehow a position given like that with the null velocities everywhere. But it is not really true. So what I would like to say is that the initial condition that we are giving to the cable is representative of the energy that with which the system is starting at time equal to 0. And into the energy there is the deformation energy associated to the potential energy associated to the deformation. And then there is the kinetic energy associated to the distribution of velocity. So here it is simple to say that we are working with zero kinetic energy and with all potential energy at the beginning with a shape that is a given shape. All right? So this, the formulation of the problem is, we have the PDA. Then we have the boundary condition, very simple, no displacement, whatever is time at the two locations, and an initial condition. In which way is evolving the system? It is very, very simple to give you the solution. The solution of this problem, apparently quite complicated, is extremely simple. The solution is, let's try to write it. So this is the initial condition, is the function f0, function of x, all right? We say that the way in which it is evolving dynamically the system with respect of this initial configuration is to have a function like that, exactly equal the same, that is 1/2, that is traveling in this way, the same 1/2 that is traveling in this way at the velocity c, at velocity minus c. So we say that those two functions at time t equals 0, 1/2 f0, let's write it like that. 1/2 plus 1/2. All right, so this object is what we call the regressive solution. This object is what we call the progressive solution. So this function is this 1/2 that is traveling in the progressive direction towards the positive x. This function is exactly the same function, but 1/2 that is traveling in the regressive direction. At time t equals 0, we have the initial condition that is w x 0 equal f0 t. And what about what is happening and for which reason? For which reason this is the solution of the problem? In which way we could say that it is true, this is the solution of the problem? Because it is very simple to show that those functions that are the initial one where the argument is not just x, but x minus ct and x plus ct, those two functions are satisfying the partial differential equation. All right? So, and we are demonstrating this in half a minute. And it is extremely simple. It is much more important, in my opinion, that you are understanding that f0 x minus ct is this wave that is traveling in the progressive direction, keeping itself equal. So we write like that, f0 So let's try to understand what does it mean having a function that is where the argument becomes the x coordinate minus c, that is a velocity, multiplying t. It means that if I'm looking to what is the configuration of the system at an instant of time t, and at the location x, these values, let's try to, the function f0 x minus ct is exactly the same that I have at a time that incremented of a quantity delta t, but at a location that is incremented delta x, as just in case it is verified that delta x is equal c delta t. So I am writing with this with this function an object that is representative of exactly the same shape, but translated of a quantity delta x when the time is shifted ahead of a quantity that is delta time is equal to delta x divided c. Or it is better to say after interval of time delta t, I am writing exactly the same shape but at an incremented location. So I am writing exactly the same function but at a location that is incremented delta x when the time is incremented delta t with delta x equal c multiplied by delta t. And in the same time, it's possible to understand that with the quantity f0 x plus ct, it is exactly the same, but I'm looking at exactly the same shape translated towards the more lower values of x when I am incrementing the time of the quantity delta t. So I'm writing exactly the same equation in a location that is shifted before of a quantity delta x equal c multiplied delta t. So we should become confident that a generic function like that is just representative of a traveling wave that is traveling at a constant velocity c in the progressive direction or in the regressive direction. So this is the physical meaning. And actually, if we are hitting the cable, it is very visual that we are looking at a perturbation that is traveling. It is our experience. In the last page of the slides, there are two links with. I suggest you to turn on those links. One of these links is showing the progressive and regressive behavior of a cable. Maybe we will have the possibility to make the experience also. But then let's say that a generic function having this shape is intrinsically solution of the partial derivative equation. For which reason? Because let's insert f0 x minus ct into the partial derivative equation. I have to write second order derivative w with respect of x. We write it as f second x minus ct equal to So I take the second order derivative of this function with respect of the variable time. We write that f z is the function, z is equal x minus ct, and we say that df over dz, we write it as f first. All right? F first is the derivative with respect of the overall variable z. All right? And so I write that the second order derivative with respect of time is minus f first. This is the first order derivative. So this is the first order derivative. First order derivative of the first of the two with respect of time. I write f first, and then I have to write the derivative of the quantity minus ct with respect of time. That is minus c. minus c, all right? Second order derivative, t square equal minus c multiplying minus c f second x minus ct, all right? So the second order derivative of the function with respect of time is equal to c square, second order derivative of the function f, all right? If I take the second order, the first order derivative of w with respect of x is equal f first x minus ct. And then if I write second order function with respect of x is equal of f second x minus t. So I do not have the trouble of taking into account that the derivative of the argument with respect of x is 1, all right? If I am taking the derivative with respect of x, partial derivative of this object, partial derivative with respect of x, the derivative of the internal variable with respect of x is 1. The second order derivative is f second. That's it. And if when we did the same with respect of time, instead we found that we found the total, the final result, that is c square f second x minus t. Let's say that we discovered that this function is actually writing that the second order derivative of this function with respect of time twice, partial derivatives, is actually equal to c square, the second order derivative of the same function with respect of x twice. All right? In case we are working with the function with this one is more simple because we don't have the problem of the minus. So if we have just to multiply c, the first step of derivative, the c another time, the second step, we don't have the minus. All right? So both of those functions are satisfying the partial derivative equation that must be satisfied. So intrinsically, a function, whatever is the function f of the argument x minus ct, is intrinsically the natural solution of the equation of waves, that is the partial derivative equation with which we are playing. So the intrinsic natural solution of this partial derivative equation is the function f, whatever function of the variable x minus ct or x plus ct. So it's the very generic solution. Then we built an example where the function that is traveling is actually exactly the initial condition that we are giving to the cable. So the problem of the initial condition that we are giving to the cable is the simplest problem that we can play with, and the solution is this object that is traveling. All right, but we didn't account for the constraints in all of that. We just considered that the function is satisfying the initial condition of position. We didn't made the check that it is satisfying the initial condition of null velocity. In order to consider the initial condition of null velocity is very, very simple. If you take the first order derivative of this function with respect of time, you have the minus here, all right? You are at the time t equals 0, this is cancelled. Then you have the second function. The second function, it is this one. it is, you take the derivative with respect of time, and you take, it is exactly equal to the first one, but with plus c. And so at the starting point, you write the partial derivative with respect of time of the sum of the progressive and the regressive. The progressive has minus c at first, the regressive has c. At the time t equals 0, you are canceling, you just have the shape. And so you have the shape, the derivative of the shape, the first multiplied by minus c, the second multiplied by c. And so it is intrinsically, it is satisfying also the condition of null velocity. So the example that we are proposing is very simple, and it is intrinsically satisfying the condition of null velocity at the initial condition. And so it is the solution, because it is satisfying the initial condition, it is satisfying the partial derivative equation, but it was stopped the registration. I don't know, but it was not working the registration, it looks to me. Anyway, is it? We were transmitting now, but before not. Let's hope. I don't know. But I started the registration at the very beginning. So what is the final result? That we checked that it is satisfying the PDE. We checked that it is satisfying the initial condition, both of display of position as the velocity. We didn't check what is happening at the constraint. At the constraint, we must satisfy a condition where, when this traveling wave is arriving at the constraint here, so this is the traveling wave that is when we are getting to the constraint, the displacement must be null. So the solution is to have exactly the same wave that is reversed. So this is the cable. So I'm showing something that is, okay, that is. So what we need is that we are mathematically representing a shape that is specular plus with minus, and specular in the other direction. It means that when this slowly decreasing, I need something slowly decreasing that is getting into here. So it is not just reversed to one side. It is two times. It is symmetrical with respect of this point. So it has two reflections, one reflection, another reflection. So we need another mathematics, another shape that is mathematically exactly equal to the first one, but reversed both plus minus with respect of the symmetry with respect of the axis of the cable, but symmetrical also with respect of the of a vertical axis that is passing to the constraint, that is getting out from here, and that is cancelling, making null the displacement here, and bringing down. So we are mathematically representing a solution that is exactly the same shape, but opportunely arranged with the symmetry, that is representative of the reflection that we are looking at when we have when we are looking at what is happening physically. Physically, we are sending the wave, and the wave is reflected by the constraint. And this reflection is mathematically represented by exactly the same shape with this symmetry that is traveling back. We stop here because we are out of time. I have to run quicker. In the slides, all of that is explained with full of details, and I also made. I suggest you to look into the WeBeep. There is another set of writing that is what I was following today. So a reduced length set of pages. All right, we stop here. We didn't finish. I'm sorry.
Una domanda sulla